Hey everyone, welcome to our channel Physics, where we actually learn physics. So in the previous lecture, we actually saw what is electromagnetic force, isn't it? We actually understood what electromagnetic force means and how important that force is for all of us, for this whole universe actually, and what is the place of electromagnetic force in physics itself. Okay, so as we saw, electromagnetic force is hugely important. It's everywhere. There is not a single place where you cannot find electromagnetic forces. So what we are gonna do is, today in this lecture we are gonna see some implications of electromagnetic force in our daily life. Okay, that means how exactly electromagnetic forces come into play in our daily life. Okay, generally if you see, we normally don't notice. Okay, in fact, these forces are invisible to all of us. Okay, because these forces only act between charged particles, and charged particles are very small. Okay, charged particles are very small, so that's why it is very difficult for all of us to actually see these forces. Okay, so that's why sometimes, and actually every time, for the normal person, these forces are unnoticed. Okay, so that's why in this lecture we are actually gonna see how important these forces are for all of us in our daily life, and where exactly we see all of these forces. So that is what our topic for today's lecture would be. Okay, the electromagnetic force in our daily life. Okay, so let's see what is it exactly. Okay, so as like we saw last time in the last lecture, that electromagnetic forces actually act between the charged particles like electrons, like the protons. Okay, protons are positively charged particles, electrons are the negatively charged particles, as we all know. Okay, so we saw last time that if the charges are stationary or moving also, then the electric forces act between them. Okay, but if the charges are moving, then the magnetic forces also act between them. Okay, so we saw last time the difference between electric and magnetic forces, that electric forces act between stationary as well as moving charges, but the magnetic forces only act between the moving charges. Okay, so that was the difference that we saw last time. But over here, okay, one thing that we can notice is these forces are only applicable for small charged particles only. Okay, and all these charged particles, electrons and these protons, okay, they are existing at the microscopic levels. These particles exist at atomic levels. If you see, protons exist in a nucleus and electrons are pretty small, they move around that nucleus. Okay, so we can see here that these particles exist at a very microscopic levels. Okay, and in fact, these protons and these electrons, okay, they are actually holding each other together. In fact, the protons are holding these electrons together. That's why the atom is pretty much stable. So we can see here at the microscopic level, the electromagnetic forces are pretty much dominant. Okay, all these microscopic phenomenons, the atomic level, the nuclear level phenomenons, are almost all because of these electromagnetic forces only. So we can see here, or we can say here, that electromagnetic forces dominate this microscopic domain, isn't it? The microscopic domain is completely dominated by electromagnetic forces only. Okay, yeah, there are other forces also, like the strong nuclear force and the weak nuclear force, which we will see later. But we can see here that electromagnetic forces are actually the ones which dominate this area, the microscopic area. Okay, so that was pretty much clear in the last lecture also. Okay, but now we are gonna see in this lecture how these forces are important at the macroscopic levels also. Okay, how these forces are important at the macroscopic levels also. That means at our levels right now. Okay, at our levels, like for us, how these forces are important. Okay, so what we are going to do here is we are going to see lots of examples. Okay, lots of examples where actually these electromagnetic forces dominate. Okay, so today we will see basically three important examples. Okay, and these three examples would be enough, sufficient for us to see how important this electromagnetic force is really. Okay, so let's see what is it exactly. So first implication of electromagnetic force in daily life is the contact forces. You can see here the contact forces. Okay, so let's see what these contact forces are. Okay, now suppose you have kept a book on a table. Okay, let's say we have a table and a book has been placed on it. Okay, that is one case. Now you are also keeping your hands on that table. Okay, now let's say there is a pen in your other hand. Okay, so in all these cases you can see that the two bodies are in contact with each other. Like the book is in contact with the table, then your hands are in contact with the table, then the pen is in contact with your hand. Okay, so over here if you feel it, okay, if you have experienced it, then you can say that every object in contact exerts some force on the other object in contact. Like for example, keep this pen in your hand right now. You will feel something. You will feel a touch. You will feel that this pen is also exerting some force on you. Or keep your hand on the walls. Try to keep it. Try to just touch it on the walls, on any surface. You will actually feel something. You will actually feel some force being exerted by these walls or these surfaces. Okay, in fact you are standing. Okay, if you are standing over there, or maybe you are sitting over there, you still feel some force from the surface, isn't it? Okay, isn't it? You actually feel some force from the surface, isn't it? So in all these cases we can see when the two surfaces of the two bodies are in contact with each other, they exert some forces on each other. Okay, when two bodies or two surfaces of the two bodies are in contact with each other, then they exert forces on each other, and these forces are called as the contact forces. Okay, these forces are called as the contact forces. Okay, and now these forces are actually very important. Okay, for example, if you take an example of this table and the book. Okay, when you keep this book on a table, why do you think that this book is able to stand or just sit over there on the table? How this table holds that book over there? That is only because of this contact force exerted by the table. When you place any book on the table exerts some force on that book in the upward direction, because of which only the table is able to withstand, or table is able to hold that book on it. In fact, when I am keeping this pen in my hands, I am able to hold it just because my hands or the surface of my hand is able to exert some contact force on this pen. When I'm standing here or when you are sitting over there, the surface just beneath my feet, okay, the surface just beneath my feet is actually exerting some upward force on me. That's why I am able to stand over here. Okay, that's why I am able to stand over here. In fact, all the objects lying on the surface are able to lie on that surface just because of the contact forces exerted by the surface on those bodies. So everywhere we can see here these contact forces come into play. Whenever you touch anything, any body, that body will exert contact force on you. In fact, not only that body exerts that force, but you also exert the same amount of force on that body. Okay, so that is how much important this contact force is. It is all over, it is everywhere. Wherever you go, whenever two objects are touching each other, this force will always be there. Okay, this force is always there. Okay, that's why we are saying here that contact forces are very important. The electromagnetic forces are very important. These are everywhere. Okay, so what I am trying to say here is, whenever two surfaces are in contact with each other, they exert forces on each other. Okay, they exert forces on each other. These forces are called as contact forces. Okay, so now we have understood what these contact forces are exactly, but we have not really understood the reason behind these contact forces. I mean, how exactly do these forces come into existence? Okay, how do they come into existence? That is the main question over here. Okay, who brings these forces into play? That is the main question, isn't it? So the answer lies over here. The electromagnetic force. It's the electromagnetic force that brings these contact forces into play. Okay, the reason behind these contact forces are nothing but the electromagnetic forces. So let's try to understand how exactly all these things happen. Okay, so let's imagine the example of that book and the table. Let's say here that the book has been placed over the table. Okay, now as we know, every material, every substance, everything in nature is made up of atoms or molecules. Okay, molecules are nothing but collection of atoms. Okay, but in general we can say everything is made up of atoms. And what are atoms? Atoms are actually made up of that nucleus which contains those protons, okay, positively charged protons, and this nucleus is surrounded by electrons, okay, which are negatively charged over here. So atom is actually made up of these charged particles, okay, and everything in nature is made up of atoms. Okay, so that means what? The book here that you are seeing and the table that you are seeing is actually made up of all these atoms, isn't it? Okay, maybe the atoms are of different types. I mean, the materials are different for the book and the table. Table is wooden. Book maybe is made up of something else. Okay, maybe there is a plastic cover or something like that. But you can get the idea that everything over here is made up of atoms. So let's say that the book is also made up of huge number of these atoms and the table is also made up of huge number of these atoms. So now what will happen? Now when you actually bring these table and book in contact, when the two surfaces are in contact with each other, actually it's not those table and book in contact, it's the atoms of book and table in contact. Okay, if you go to the microscopic levels, then it's actually the atoms of book and atoms of table in contact with each other. Okay, now over here, when these atoms of book and table will come close to each other, what they will do? These are made up of those electrons and protons, and as we all know, charged particles exert forces on each other, isn't it? Charged particles exert forces on each other, isn't it? Basically, atom has that nucleus at the center and electrons outside. So same with the book and same with the table. So what will these outer electrons do? Okay, outer electrons of book and outer electrons of the table. What will they do? They will exert forces on each other. Forces of repulsion on each other, isn't it? Okay, so that is how the contact force actually arises, isn't it? That is how the contact force actually arises. This is only because of the electromagnetic forces of repulsion between the atoms of the book and the table. Okay, this is just one example, but in all cases, wherever two surfaces are in contact with each other, then the atoms of the two surfaces at the surface exert some force of repulsion on one another. And that is how the contact forces arise. Okay, so we can see here, it's nothing but the electromagnetic force at work, isn't it? Okay, so we can see here, all these phenomena that we see, they are actually arising due to this electromagnetic force. Like we are standing right now, the surface beneath us is exerting electromagnetic force on us. That's why we are able to stand. Okay, that's why we are able to stand. Otherwise, it is difficult. When you hold something, okay, when you are actually holding something, it's actually the electromagnetic force, okay, that you exert on that object, because of which only you are able to hold that object. Otherwise, it's difficult. Same here. Okay, it's not only you keep it like this, okay, even if you keep it like this, still there is a electromagnetic force, okay, because of which it happens. So every time you are holding something, it's nothing but the electromagnetic force which is actually holding it. Okay, so that's how important this electromagnetic force is for us. That's how important these contact forces are for us. They are hugely important. They are everywhere. Okay, because we are always in contact with something. So these contact forces will always be there. Definitely. Okay, so this is the contact force. Now actually, just now I said that contact forces always come into play when the two objects, okay, are in contact, or the two surfaces are in contact. So for example, I will show you here. Let's say that the two surfaces of the two objects are in contact. Let's say, for example, this is a second object placed on the first object. Okay, yeah, so here are two objects, okay, placed on one another. Okay, here you can see two objects in contact. Now what will happen here is, this object that you see beneath will exert some force in the upward direction. Okay, it will exert some force in the upward direction, and a same amount of force will be exerted in the downward direction by this body above. Okay, so the two bodies exert equal amount of forces on each other. Okay, the two bodies exert equal amount of forces on each other. The thing here to notice is that the contact force, okay, the contact force is perpendicular. Okay, you can see here the contact force is always perpendicular to the surfaces in contact. Okay, they are always perpendicular to the surfaces in contact. Okay, so perpendicular we also call as normal. Okay, sometimes we call perpendicular as a normal. So that's why these forces are also called as normal forces. Okay, these forces are also called as normal forces because we call perpendicular as normal also. Okay, so this is one aspect over here, but over here I can say that the contact forces are not always perpendicular. Okay, the contact forces are not always perpendicular. In some cases, okay, in some cases the contact forces are parallel to the surfaces also. Okay, in some cases the contact forces are parallel to the surfaces also. For example, the case of a frictional force. Okay, frictional force is again a contact force. Okay, frictional force is a case of a contact force itself, but this contact force, the frictional force, is actually parallel to the surfaces in contact. Okay, for example, you can take an example of this walking. When you are walking actually, okay, see, how do you walk? You have to exert some force. Okay, you have to exert some force on the floor. Okay, and the force that you apply is not exactly vertically downward. If you apply a force vertically downward, then the floor will exert force in the vertically upward direction, so you will just jump. To walk, you have to apply a force little bit tilted. Okay, it should make certain angle with the vertical line. Okay, so then only you are able to walk. Okay, now the force that you apply over here, it has two components. One is a vertical component and other is a horizontal component, and the horizontal component is the one which helps us in walking, and that is nothing but this friction. Okay, over here the friction arises. Okay, so you will learn about this frictional force later in other chapters, but you can see here that the contact forces are also parallel to the surfaces in contact, not only perpendicular. Okay, so this is, we can say, all about the contact forces. Okay, so we have seen the first implication. Now let's go to the second one. Okay, the second one is nothing but the tension in string, or you can say ropes. Okay, the tension in string or ropes. Okay, that is the second implication of electromagnetic forces. Okay, so what is this tension in string? Okay, you must have seen the strings. Okay, see, when you stretch those strings, okay, when you apply some force, like for example the tug of war game that you might have played actually. Okay, so in that game what we do, the two teams actually pull that string towards themselves. Okay, one from that side, other from this side. So in that case the rope in between is actually stretched. Okay, it's very tight. Okay, it's very tight. So such a string, okay, or such a rope is said to be under tension. Okay, said to be under tension. Okay, so a string which is very tight, okay, stretched, is said to be under tension or inner tension. Okay, so that is tension, but we are talking about the tension force here. Okay, so let's try to understand what is this tension force. To understand this, I'm going to talk about three cases here. Okay, I'm going to talk about three cases over here. For example, in the first case, let's say we have one block. Let's say we have one block, and on this block, let's say we apply some force towards my right side. Okay, towards my right side. Okay, now we know if we apply a force in this direction, definitely the block will accelerate in this direction, assuming there is no friction at all. Okay, so block accelerates in this direction. Now let's say on the same block I now apply force in this direction towards my left. Okay, same block, now we are in the case 2, force is applied towards left. So definitely what will happen, the force will accelerate this block, the block will start accelerating. Okay, so now from these two cases we can see here that whenever there is a net force acting, on any body, the body just accelerates, whether it's a force in this direction, that direction, this direction, any direction. If there is a net force, the body will definitely accelerate. Okay, now let us assume a third case. Okay, let's say we have the same block again, but now there are two same forces acting on that body. Let's say we have two forces, one acts towards this right side, one acts towards left side at the same time. The magnitude of the force is same. Let's say both are 5 newtons, for example. Now from our common experience, we all know if the same forces are applied in the opposite direction on the same body, the body won't actually accelerate or move. For example, the case of a tug of war. See, when the two teams pull with the same force, okay, from both sides, the rope does not move at all. Okay, but when one of the teams gets tired, then it starts exerting less force. Then the other team exerts more force, so it can pull it. But when the two forces are equal, the object does not accelerate at all, isn't it? It will not accelerate at all. So what I am trying to say here from these three cases, okay, what I am trying to say here from these three cases is that if there is no net force acting on any body, there will be no acceleration. Like in the case 3, the two forces were acting in the opposite directions, they cancelled each other, so there was no net force. So if there is no net force, there will be no acceleration. Okay, so now just keep this in your mind. It's a very golden statement that if there is no net force, there will be no acceleration at all. Okay, now there is no relevance actually between these three cases and the tension in the string. Okay, but it was very important to understand for all of us that if there is no net force, there is no acceleration. Okay, so now let's see what this tension is actually. Now let's assume that we have one string. Okay, let's say the string has been tied to a rigid support. Okay, and at the other end, okay, at this other end, let's say there is one block hanging from this string. Okay, so we have a rigid support to which a string has been tied, and let's say a block with some mass has been tied at the end of this string. Okay, now if you look at this block, okay, with some mass, there will be some force on this block. Okay, I'm not talking about the tension right now, I'm not talking about a string or anything, but any object like this pen, okay, it has a force on it called as the gravitational force that acts always downwards. So on that block also there will be some force, and that will be in the downwards direction. That is nothing but the gravity. We call that weight of that object, weight of that block. Okay, and that will be equal to nothing but the mg. Okay, mass into acceleration due to gravity. Mg is the weight. So there is a force now on this block. According to our previous discussion, just now we saw whenever there is a force, there is an acceleration. Now here is a force on this block. Then why does it not accelerate? Isn't it? There is a force, weight. Then why does it not accelerate? Why is it still there, hanging there? You might say, no, it's tied. So what, it is tied? What is this string doing? Isn't it? Have you ever asked this question? tied means what? What is this string doing actually? Isn't it? That is the main question. We see here that there is a force on this block. According to our discussion, if there is a force, there should be a acceleration. The block should fall down. It should go down. Then why is it not going? It is still there. Still there, that means there is no acceleration. Acceleration is 0. And in the case 3 actually we saw the body does not accelerate if there is no net force. That means over here on our block there is no net force. That's why it is not accelerating, isn't it? Our block is not accelerating because there is no net force. That can be the only reason, because bodies don't accelerate if there is no net force. So same must be here. But we see there is a force. There is a force, isn't it? That is downwards. So is there any other force that is cancelling this out? This downward force is being cancelled by some other force? Is it? Is there any other kind of force? Yes. Yes, there is actually. There is a force. There is a force exerted by this string on this block, and this force is nothing but the tension force in the string. Every string exerts some force called as the tension force on any object tied to it. Okay, every string exerts this force on any object that is tied to it, to its end. Okay, it's not always this object which is tied. Sometimes we may be pulling it. Okay, we may be pulling it, isn't it? So in that case also the string exerts the tension force on the agency which is pulling it. Okay, like right now I am the agency who is pulling it. So string will exert that tension force on me also. Okay, so we can see here that in the string there is always this tension force, because of which only all these blocks, all these heavy masses are able to hold on. Okay, that's why the string is actually able to hold these blocks. Okay, and if you know, the strings are able to hold a very large masses. Okay, if you see manufacturing industries over there, you know, heavier masses can be held on to by using these strings. Okay, so this tension force plays a very important role all over the world in manufacturing industries, everywhere. At our homes also we use these strings. Okay, everywhere. Okay, so this is nothing but the tension force. Okay, so over here there is a block, there was a gravitational force due to which it should fall, but now it is not falling just because the string is exerting upward tension force. Okay, now again the question arises, how? Where does this tension force come from? Isn't it? Where does this tension force come from? Again the answer lies over here, the electromagnetic force itself. Okay, now you may say, how exactly does this happen? The answer is very simple again. See, now if you see, how exactly do you hang this block to a string? There can be many ways actually, out of which I am showing you two cases. Okay, how you can actually tie this block. Either you can use this hook, okay, or you can just roll over that string, okay, and just tie it. Okay, that's it. That's how we do it actually. Okay, now in either cases, okay, if you take any case, in all cases there will be always this electromagnetic force, because see, the block is made up of what? Atoms. Atoms are made up of electrons, protons. The string is also made up of what? Electrons and protons. Okay, now if I take the example of that hook, so if you see, there is a hook like this, okay, hook like this, and from that hook we just insert that string. Okay, we just insert that string through that hook. Okay, and what happens, the string is now beneath the hook. Okay, beneath the hook, just like imagine the case of a book on a table. So it's a hook on a string. Okay, the end of a hook on that string now. So again, what will happen, the electromagnetic forces between the hook atoms and the string atoms will now come into play, and they will exert forces on one another. Okay, these atoms will exert forces of repulsion on one another, and the force exerted by the string on that hook in the upward direction will hold this block at its position. Same thing goes when we just roll it over. Now you can see, when you roll it over, the string is now beneath that block. Okay, so what will happen, the string will exert upward force on that block. Again, the electromagnetic forces themselves, the forces between those atoms of the string and the atoms of the block. Okay, so that is what happens over here. But these two forces that I talked about do not contribute heavily in holding these masses. Okay, I mean, using these forces that I just talked about, the mass cannot be held on to by the string. Okay, these are just the contact forces actually. These are just contact forces. So these are generally very small. So their effect is very small. Even though they are there, okay, even though they are present over there, they are definitely exerting a force in the upward direction. But the magnitude of these forces is very small. That's why it is not going to hold that heavier mass, okay, onto that string. So the question is, then what is the exact reason behind holding these masses? Okay, the answer is over here, the tension in the string. Okay, over here, what matters is the tension in the string. So now we will answer exactly what is tension in the string. Okay, so as we all know that any material is made up of atoms, so definitely the string is also made up of atoms or molecules, right? So all these molecules are bound to one another with some atomic bonds, right? There are atomic level bonds between these atoms and the molecules. Okay, so that means these atoms are bound to one another with some force. Okay, with some force, there is some atomic level bond, okay, which plays a very important role. Now the thing is, the atoms in any material or the molecules in any material are fixed at their positions. They don't change their positions. Okay, if you try to just bring them closer, they will repel one another. If you try to get them far away from each other, again they will attract one another. So they want to remain at their original positions. They don't want to change their positions. Okay, what they do is, when you just increase the distance, when you try to increase the distance, they will attract one another. There will be an attractive force that will come into play, and when you will try to get them closer to one another, they will repel one another. Okay, this is not what I am saying, this is what experimental data and the experimental evidences are saying. Okay, this is what so far we have observed, okay, experimentally. We have the proofs for this also. We have lots of analysis, lots of graphs regarding this. Okay, so this means whenever you will try to pull these atoms apart, they will exert attractive forces on one another. Now look at the case of this string. What is happening in the case of a string? In the case of a string, we are doing the same thing. When we are just hanging some mass to that string, actually we are exerting a force in the downward direction on that string, and in that way we are actually trying to pull those atoms apart. Okay, it's like we are stretching that string, so the atoms are just being pulled a little. Okay, even though that distance is not that much, but at the atomic level it matters. Okay, that distance is something. There is some change in the distance between the atoms. Now what will happen if this happens? If you increase the distance, okay, between the atoms, again the atoms won't like it, because atoms want to be at their original positions, at their original states. So what they will do? They will exert attractive forces on one another, isn't it? So this is what happens when you hang some mass to a string. When you hang some mass to a string, actually some attractive forces between the atoms of the string come into play, because you are actually pulling these atoms apart and they are trying to attract each other, and this happens all over the string. Okay, the same thing happens all over the string, because all the atoms in the string are being pulled apart from each other. So that's why they will attract one another, and because of this what will happen? Because of this there will be an attractive force coming into play. Okay, and the resultant of all these attractive forces among all the atoms of the string is nothing but the tension force, and this is the force because of which the string is able to hold on to that mass. Okay, this is why the string is able to hold that mass to itself. Okay, that's the main reason over here. Okay, this is the main reason why all these things happen. Okay, just check, when you just when you just hang some mass. Okay, when you just hang some mass, what is actually happening over there? It's nothing but you are trying to pull those atoms apart, and if you do that, they will exert attractive forces on one another, right? Because they want to be bound to one another, right? This is how everything is made up, by bounding, right? By this bond only. So that's why over here this attractive force will come into play, and the resultant of all these attractive forces, okay, all over the string will produce a net effect of holding that mass, and we call this resultant force, the resultant attractive force among all the atoms, as the tension in the string. Okay, we call this as the tension in the string. Okay, so this is what tension in string is all about. Okay, and this is the reason why all these things happen. And again you can check, this is all because of the electromagnetic forces. Okay, electromagnetic forces at the atomic level. Okay, so this is the tension force actually. Okay, now we move to the third one, that is called as the spring force. Okay, the spring force. Now you all might have seen these springs. Okay, springs are used everywhere. Okay, you all have seen the springs, isn't it? They look something like this actually. Okay, these are used everywhere, like in your bikes. Okay, there are shock absorbers. Okay, there are some shock absorbers in the front tires and at the back tires also. Same in the cars, there are shock absorbers. Again, there are springs inside actually. Okay, everywhere we use these springs. Okay, there are chairs in which springs are used. Okay, office chairs, then lots of other places where springs are actually useful. Okay, like in the smallest of the pens, you might have seen in the pen itself, that TikTok pen. Okay, that actually has that small spring. So springs are used everywhere. Okay, so now we will understand what is this spring force. Okay, now actually the spring comes into three states actually. It has three states. Okay, one is its natural state, second would be its compressed state, and third would be its elongated or stretched state. Okay, so these are three states: the natural state, the compressed state, and the elongated or stretched state. Okay, so What is this natural state? First of all, it's nothing but definitely when the spring is neither stretched nor compressed. Okay, when it is neither stretched nor compressed, that state is called as the natural state. Okay, and the length of the spring in the natural state is called as the natural length of the spring. Okay, then we can compress it, we can stretch it. Okay, now suppose we have compressed it. Let's say we have compressed the spring. Now we have experienced all this actually. When you compress it, okay, if you have not compressed, just go and compress the spring and check what happens. When you do that, now you are the agency actually. You are the agency who is applying this force for compression. Okay, so when you do that, the spring actually exerts some force on your hands also. Just check that. Okay, why it does that? It's very simple, because the spring actually wants to regain its original, the natural state. It does not want to be in that compressed state. It wants to come to its natural state. So when you compress it, it will try to return there to its natural state. Okay, so that's why it will always exert that force on the agency which is applying this compression force. Now let's say you have stretched it. Okay, let's say you stretch that spring. Again, go and experience the same thing. When you do that, the spring again exerts some force on you. It again exerts some force, but now in this direction. Okay, if you stretch it, the spring will exert force in this direction. Okay, so again, why? Just because the spring would like to come back to its original natural state. It does not like to be in this compressed state. Same with this stretched state. Okay, so the spring neither wants to be in a compressed state nor wants to be in a stretched state. It wants to return to its natural state, and that's why whenever it is compressed or it is stretched, it will exert force on the agency which is applying this external force to regain its original state. Okay, so this force exerted by the spring, okay, this force exerted by the spring on the agency which is applying this external force is called as the spring force. This force is called as a spring force. Okay, now this spring force is actually dependent on how much you are compressing it or how much you are stretching it. Okay, it depends on that change in length. More you change the length, more will be the force. Okay, let's say initial length was 10 centimeter, and if you change it to, let's say, 8, that means you have changed it by 2, so the force will be less. If you change it to 5 centimeters, now there is a change in length by 5, so now the force will be higher. Same when you just stretch it. Okay, let's say initially the length was 10, now you stretch it to 12, the force will be less. If you stretch it to 15, now the change in length is more, so the force will also be more. Okay, so this is what actually happens in the case of a spring. Okay, so spring always applies this force, and remember, the spring force is always opposite to the applied force. Okay, always opposite to the applied force. That is the main property over here. Okay, now every spring has a different property actually, and that depends on how it is made, the material from which it is made, etc, etc. Okay, that's why, see, if I take this one spring and the other spring, if I elongate the both springs by the same amount, the two springs will not exert same forces, because they may be made up of different materials, the construction may be different, structure may be different. So that's why every spring will exert different amount of spring force. Okay, so that's why to characterize these different springs, we associate one number to every spring. We associate one number to every spring, and we call that as spring constant. We call that as spring constant, and it is denoted by K, small k. Okay, so every spring has a different spring constant on which the force of spring depends. Okay, so this is spring. Now again the question is, how does this spring force arise? Where it is coming from? That is the main question. Again the answer goes here, the electromagnetic force. Now see, the spring is definitely made up of some metal. Okay, generally we make it by some metal actually, or maybe some other rigid material. Okay, maybe some hard plastic, some fiber or something like that. Okay, but mostly we see a metallic springs only. Okay, so now you know the properties with those rigid metals. Okay, not metals, not every time metals, sometimes some other rigid materials. So you know the properties of these materials, that the atoms, see actually this material, definitely they are made up of atoms. The thing over here is, for metals, the distance between any two atoms that you take in the material is constant. Okay, the distance between the atoms is constant. The atoms are located at a particular places and they are fixed at their own places in the material, and they don't like to change their places. They are pretty much fixed over there. They are rigid actually. They don't want to move from there. The bonds between the neighboring atoms are pretty strong. They don't want to break it. It's very difficult to break it actually. So now for example, when you compress the spring, okay, when you compress the spring, what you are actually doing at the atomic level is, you are actually bringing these atoms closer. You are changing the distance between the atom, decreasing it actually at the atomic levels. And this is something that the atoms won't like. They don't want to change their positions. They want to be there only. Okay, so what will happen in that case? The atoms, when they go closer to one another, they will start repelling one another. They will just start to repel one another. Definitely this force is nothing but the electromagnetic force, because at the atomic level the charges are there which are exerting this force. So over here, when you compress the spring, the atoms go closer to each other and they exert repulsive electromagnetic force. And that is the reason why the spring exerts this opposite force, okay, when it is compressed. And same thing happens when you stretch it. When you stretch any spring, basically you are increasing the distance between the two atoms. Now again, these atoms won't like it. Why? Because they have a very strong bond between them. Very strong bond, and now you are trying to, break that bond apart. Okay, you're doing something like that. You are actually breaking that bond, trying to break that bond, and these atoms won't like that. So when you just pull this spring, you are actually bringing those atoms far from each other. Okay, so they will not like it. So in that case, some attractive force comes into play, which tries to bring those atoms at their original places. And this is how this spring is able to exert that force in the opposite direction. When it is stretched, it exerts force in this direction. That is because of the atomic level attractive force. Okay, so this is how actually the spring force comes into play, comes into existence. Again, due to this electromagnetic force. And we all know how important this spring force is for especially the manufacturing industries. All over this is used everywhere. cars, it may be, or in fact the huge machineries in the industries, they use this springs. So spring forces are very, very important. Okay, so in this way we have seen the implications of electromagnetic force in our daily life. We saw three examples: the contact force, the tension force, and the spring force. Okay, so this is all for today. Okay, this is all in this lecture. I hope you have enjoyed this. I hope you have learned something from this. Okay, so I would say this is all for today. We will meet in the next lecture, and we will have some more fun physics actually. Okay, so thank you so much for listening. Thank you so much for joining. Have a nice day. Yeah, bye bye. Thank you.